talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolvin. Today we're going to talk about free fall and how fast things are traveling and how you figure that out in free fall. And this is part 5 of our linear motion series. So, falling objects. Most falling objects in the real deal world experience air resistance. They move through the air, there's a little bit of friction with the air, slows them down a wee bit. Well, that's not really good enough for physics people because sometimes they like to talk about how objects fall without that air resistance, because the air resistance adds a little bit of a tweak there, a little bit more difficulty. So the special physics case in the special physics fairy world of physics is free fall. It's when an object is in free fall, when only the force of gravity is affecting the object's movement. There is no air resistance. Usually things fall freely in a vacuum. Now, I'm not talking about your mom's Hoover, or Dyson. That's not that kind of a vacuum. A vacuum in physics means that it's a space that all air has been taken out of it. So if all air has been taken out of a space, if something falls through it, the only thing that's going to be pulling it toward the center of the earth is gravity. Okay, so your book talks about this thing called elapsed time. It just means that time's passed since the beginning of the fall. So if something has been falling 6 seconds, the elapsed time is 6 seconds. It's not a big, huge, hairy thing. It's just your book uses a little bit different term. So during each second of free fall, the instantaneous speed of an object increases by 9.81 meters per second. Wow! Almost 10 meters every single second that it falls. That's kind of crazy. So if the change in speed is in meters per second and the time interval is in seconds, then the acceleration is in meters per second squared. Okay? So for free fall, we use a special, for if we're talking about acceleration due to gravity, there's a couple of different ways that they do it. I usually use A with a little g, saying it's a special kind of acceleration. It's acceleration due to gravity. Your book uses just a lowercase g. I'm not really a fan of the lowercase g because it makes it seem like it's not something related to acceleration. So whenever I do acceleration due to gravity, I always use an A with a little g next to it. But be aware your textbook is going to use the g. So this acceleration is only due to gravity. Although acceleration due to gravity varies in different parts of the world, its average value is 9.81 meters per second squared. That's going to become like a little song in your head because we use the acceleration due to gravity a lot in this class. So the sooner you learn it, the better it is. On your sheet of formulas, I think I have acceleration due to gravity being 9.81 meters per second squared, but it would be a lot easier if you just remembered it, because you'd have to look it up like a bazillion times before you leave this class. So, instantaneous speed of an object falling from rest in free fall can be calculated using either of these formulas. They're really, let's be honest, they're really the same formula. So I like to call these the VAT formula, this formula the VAT formula, because it's really easy to remember. It's just a little variation of the A equals V divided by T formula. This one gives you velocity directly. So the VAT formula, going to use that a lot too. Or if you're a fan of the lowercase g, it's the V equals GT formula. So velocity equals the acceleration due to gravity times time. Both of these mean exactly the same thing. I like this one because it actually forms a word, so it's easier to remember that way. So the A sub g, or the g, is the acceleration due to gravity. T is the time that's passed since it started. Letter V represents both speed and velocity in this situation. So the average speed of any object moving in a straight line with a constant acceleration is the average of the initial speed and the final speed. Well, that kind of makes sense. If I'm going to average two of your grades together, I'm going to add them up and divide by 2. Um, so average speed is going to be the initial speed divided plus the final speed divided by 2. So that just explains how to do average speed, another way to figure out average speed. So if you wanted to find out what the average speed of a freely falling object in its second of fall is, and this is not actually correct, so we're going to skip by this. Okay, so let's talk about rising objects. For an object thrown straight up, here's kind of a cool thing. Yes, I know this is like brand new to you. For an object that's thrown straight up, it moves upward. Oh my gosh, how crazy is that? So here's my husband Bob on a cliff, and he's throwing a cantaloupe up in the air, and it goes up for a little ways, and then it kind of stops a wee bit, and then it falls down past him on the cliff. So at the highest point, the object is actually changing directions. It stops for just a split second. So at that particular moment, the instantaneous speed is actually 0. Now, the acceleration due to gravity is not 0. It's only the instantaneous speed. The acceleration due to gravity is still 9.81 meters per second squared. Doesn't matter if you're throwing it up or it's falling down or if it's stopped here at the top. It's still on the earth. Gravity doesn't shut off. If acceleration due to gravity was 0 at the very top, every time somebody threw something into the air, we'd all float off the earth momentarily and then fall back down. Weird, okay? So don't mess that up. Instantaneous speed and velocity at the very tip top is 0. Acceleration is still 9.81 meters per second squared. So as it falls downward from this height, it's actually falling as if it were dropped from that height. So we really have two kind of problems here, where the cantaloupe is slowing down as it goes further up until it stops. And then that's one problem. And then the second problem is if it were falling from that height and coming back down. So here's kind of the interesting thing. At identical heights during the path of this cantaloupe or anything that you throw up, it's going to have identical speeds. So right here, whatever speed that you throw it with, in this case it happens to be 30 meters per second, once it goes up, stops momentarily, and then falls down again, once it gets to exactly that same height, it's going to have the same speed. Okay, that's really important. So like after 1 second, if the velocity is 10 meters per second going up, as it comes back down to that same height, it's going to have exactly the same speed. Okay, so velocity is going to be different because the velocity when you first start out, the velocity is upward, right? And down here, and when it comes back down, it's going downward, so the velocity is down. So even though the speeds are the same, the velocities are different because they have different directions. They're going in the opposite direction. During each second, the speed or velocity changes by 9.81 meters per second downward. So the acceleration is pulling it down to Earth. So as this thing rises up, every second it's rising, it loses 9.81 meters per second until it finally gets to the top and it stops. And then when it's falling, it's gaining 9.81 meters per second for each second that it's falling. That's it for this time. Thanks for joining me. Have a good day.